Okay, take a look at number 4, and let's go through our list of things that we consider before immediately jumping to an inverse trig antiderivative. So, can the power rule apply with this integrand? No. Is this integrand a derivative that you're familiar with? No. Do you see an embedded function here, a composite function where maybe you would do a u substitution? No. Can you maybe consider a u substitution for the entire denominator? Well, let's take a look at that one. So if we did u equals 1 plus x squared, hey, look at this. Du is equal to 2x dx. And you've got an x dx in this problem. So this actually is not a problem involving inverse trig whatsoever. And so that's why it's so important in a lot of these to always kind of start with the basics and then get more complex or consider more complex approaches as you go. And so if du is 2x dx, we would put a 2 in the integrand and a 1/2 in front. I would change this problem into 1/2 integral. Remember, when we do definite integrals involving u substitution, we end up changing the limits of integration to be in terms of u, or at least that's how I've done it in this class. And we'll have du over 1 plus x squared is my u. So let's see, negative root 3, this is where I go into the ux equation. If x is negative root 3 squared is 3, plus 1 is 4. And then 0 squared is 0, plus 1 is 1. And so I know it's kind of weird to see that the smaller number up top, but that's what we have here. I'm not going to switch them because that would introduce a negative here, and I'm just going to leave it as is right now. So this is going to be an entirely new problem from this point, and the answer is going to be 1/2 times the natural log of the absolute value of u, where u is going from 1 to 4. And so I end up getting 1/2 times the natural log of 1 minus the natural log of 4. And the natural log of 1 is equal to 0. And so this can be simplified as just negative 1/2 times the natural log of 4. So that's my answer to question 4. And by the way, remember, when you have a definite integral, you can plug this into your calculator. You can put in your lower bound, you can put in your upper bound, and the calculator should even shade the region and tell you specifically what you're looking at. And since in this case it looks like we have a negative result, that means there's more area below the x-axis than there is above in this interval from negative root 3 to 0. Okay, question 5. This one we've got 1 over the root of 25 minus 4x squared, and a big difference between this question and the one that we just did is you might be considering again a u of 25 minus 4x squared, but in that case, wouldn't your du be 2x? Or I'm sorry, not 2x. Your du would be 2 times 4x, so your du would be 8x if you were considering the inner part of the composite function as your u substitution. However, you can't have a du like that in this problem because we only have constants here. And so when I see those types of u substitutions failing, this is when I'm automatically thinking, okay, this is probably an inverse trig problem. So this lines up a lot with the Arcsine antiderivative, and so let's go back and just look at that one real quickly. The Arcsine antiderivative was du over the root of a squared minus u squared equals arcsine of u over a. Okay, so I'm just going to note that right here, that the integral of du over the root of a squared minus u squared is equal to arcsine of u over a plus c. So this looks like the type of setup that we have. And if my a squared is 25, that means a in my problem is 5. And if my u squared is 4x squared, then that means u would be equal to 2x. But I still need to get du, so du would be equal to 2 dx. So I adjust, and my problem becomes 1/2, and I'm going to change those limits of integration in just a second, but this becomes 2 dx becomes du, And then the denominator is the root of 5 squared minus the quantity 2x squared. So that's exactly what I have when I have the root of a squared minus u squared. And that's exactly how I want to approach a lot of these inverse trig antiderivatives, is I want to get exactly what the formula says I should have. But let's get these new limits, and then once we get the new limits, we can evaluate this. So, so what we have here is, let's see, we had an x of 0, right? So if my x is 0, my u is now 0. And if my x is 1, my u is now 2. But this is an entirely new problem at this point, okay? And so, based upon that, my answer is going to be 1/2 times the arcsine of u over a going from 2 to 0. So it's going to look like this. 1/2 times the arcsine of u over a going from where u is going from 2 to 0. So if you want, you can actually plug in your a value right now, or we can plug in the a value at the end. But u is what's going from 2 to 0, so let's plug that in. We'll get 1/2. Sometimes I'll take the 1/2 would be part of each term, so a lot of times I'll just take the 1/2 out in front. I'd have 1/2 arcsine of 2 over a minus 1/2 arcsine of 0 over a. And if you're doing the arcsine of 0, if you did the inverse sine of 0, you're saying the sine of what angle gives you 0, and the actual answer here is 0. So this term just becomes 0, and your answer is 1/2 arcsine of 2 over a. But our a value in this problem is 5. So the final answer would be exactly what I have right here. Okay, and again, definitely check this in your calculator. Make sure you get the same decimal approximation that we are getting right here. But that is it. That is it for question 5. Okay, number 6. Last one. We've got dx over x squared minus 4x plus 13. And you'll notice you can't do a u sub for that denominator. A lot of those old strategies will not work. But this is also not in the form of one of those inverse trig problems. And so what we need to do is we actually need to get it in that form sometimes. And so what we're going to do is we are actually going to, in a case like this, complete the square in the denominator so that we can have a quantity squared plus a constant, and so that it can look a lot like the formula for the antiderivative, where the solution would lead to an arctangent. And so if we just pull that back up from the other side, the antiderivative of du over, it's u squared plus a squared, is equal to 1 over a times arctan of u over a plus c. So we're going to try to get it in a form like this, where it's du over u squared plus a squared. So we're going to complete the square in that denominator. So if I'm going to complete the square in that denominator, then that means I'm going to separate the 13. I'm going to move the 13 down here a little bit. And I'm going to take half of the x term, so half of the coefficient of the x term, so negative 2, and square that. So I'm going to add 4. But you can't just add 4 into the problem. You have to keep things balanced. So I'm also going to subtract 4. So now this becomes the integral of dx over, this is my perfect square. X squared minus 4x plus 4 is x minus 2 squared. And then the negative 4 and the positive 13 combine to give us a plus 9. So now this is kind of in this setup right here, where our u would equal x minus 2, our a would be equal to 3, since a squared is equal to 9. And notice if we do use this setup, that du is just going to be equal to 1 dx. So we already have that in there. So this integral becomes the integral of du over u squared plus a squared. So it's actually pretty easy from this point, but the initial setup to get it to look like an integrand that will lead to a inverse trig antiderivative, that's the tough part. The completing the square was definitely the tough part. So this becomes 1 over a arctan of u over a and then plus c, and I'm just going to plug in for my u and my a. So final answer, 1/3 arctan of x minus, I'm sorry, that's x minus 2 all over 3, and then plus c. So there we go. Okay. In the very next video, I'm just going to wrap this up by walking through a few more exit problems, a few more practice problems, and then hopefully you can tackle this last homework assignment. Congrats, you've made it.